Okay, so what I want to talk about now is polynomial and rational inequalities. And so the idea is our goal is to answer a question like this. A question like, something like this. And the way that we can handle this inequality is you could try to play around with it and plug in different x values and see when it actually works. But the easiest way is to kind of think about what a function looks like in general. So this is a function, and what a function looks like is we can have something like this. Okay. Something like that. We could also have, like, maybe I'll put like a little hole right there. And the idea is that in the inequality, what it's saying is, so if this is the function right here, then it's asking for when it's bigger than or equal to 0. So we could actually look at it. When is it bigger or equal to 0? It's right here. It's bigger than or equal to 0 right there because it's above the x-axis. It's right here. And then it's right here. So how can we find those places? Well, one of the easiest ways to find these places is to find kind of like the endpoints. This endpoint takes place when we cross the x-axis. This endpoint takes place at an asymptote. This one takes place when we cross the x-axis. This one takes place at a hole. This one takes place at an asymptote. In other words, the only times that you're going to end an interval of being above or on the x-axis is when we cross the x-axis, we have an asymptote or a hole. Now these things take place, so when we cross the x-axis, that's an x-intercept. And when we have an asymptote or a hole, that's a domain issue. What that means is, if we could find all the places where we cross the x-axis, or where we have a domain issue, then that tells us where the possible endpoints are for the intervals of being above the x-axis. And if we know where the endpoints are, then we can just test in between the endpoints to see when are we above the x-axis. So with this example right here, we're going to go through and see if we can figure out what the zeros are and what the holes are, or the domain issues. So for the x-intercept, we're talking about when this thing is equal to 0. One is x squared minus 5x plus 6 over x minus 4 equal to 0. You could multiply both sides by x minus 4 and see that this amounts to saying when does x squared minus 5x plus 6, when is it equal to 0? And we can factor this into x minus 2x minus 3, when is this equal to 0? And that's when x is equal to 2 and x is equal to 3. And then here we have a domain issue when x is equal to 4, because you're not allowed to divide by 0. So in other words, 2, 3, and 4 are our possible endpoints. So if we put this on a number line, so on a number line, at 2, 3, and 4, those are the possible spots where the parabola, or in this case it's actually a rational equation or expression, is bigger than or equal to 0, it's going to have endpoints at 2, 3, or 4. So what we do then is we know that if it's staying above the x-axis right here, we should see that by plugging in a value. So we're going to pick some values. We're going to pick values in each of the intervals and see whether or not this segment is above the x-axis or below it. If this segment is above the x-axis or below it, and so on and so forth. So what we'll do is we'll plug in something like, maybe I'll plug in 0. So I'm going to put my picks above 0, maybe 2.5, maybe 3.5, and maybe 4.5. Then I'll plug it in. So when I plug in 0, I get 0 minus 0 plus 6, I get 0 minus 4, so I get 6 over negative 4, which is negative 1.5. So I'm going to call this my f of x. F of 0 is equal to negative 1.5. So that means it's negative. I'm going to put a negative underneath that. When I plug in 2.5, so f of 2.5, I get, maybe it's easier to see f of x as something factored out. So remember, this is x minus 2, x minus 3, x minus 4. What I'm going to get is I get 0.5 multiplied by negative 0.5 all over 2.5 minus 4 is negative 1.5. I could multiply this out if I wanted to, or I could realize a positive times a negative is a negative, and a negative divided by a negative is a positive. So I don't even need to know what it is. I do know that it's positive. If I look at f of 3.5, I'm going to get 1.5 times 0.5 over negative 0.5. Positive times positive is positive. Positive divided by negative is negative. So it's negative. And if I plug in f of 4.5, I'm going to get 2.5 multiplied by 1.5 over 0.5. Positive times positive divided by positive is positive. Now remember from before, we knew that 2 and 3 were both when it was equal to 0. And since we're looking to or equal to 0, those are two good examples of when it's equal to 0, so we use them. We also know that between 2 and 3, it's positive, which means it's above 0, greater than or equal to 0. And we know from 4 on, not including 4, because 4 is a problem with the domain, that that's also positive. Now if I shade in the regions, since I'm greater than or equal to 0, I'm looking for things that are positive. Right? When I plug in f of something, I'm getting the y value. The y value being positive means that it's going to be above the x-axis, so it's up here. So that means if it's positive, it's greater than or equal to 0. So then I want the positive things, and if I shade them in, I actually see exactly what the solution is. The solution is from 2 to 3, union, square bracket on the 3, union 4, parentheses, to infinity. That's my solution for this particular problem. And in general, that's the way it's going to work. We can just run through. So you're going to find the domain issues and find the holes, put them on a number line, find test points in between, test those points and see what the actual value is, and then see if it's positive or negative, and then compare it to what the actual inequality is. So I'm going to do through another example. I'm going to write down the steps then, and run through one more example. So the steps are find x-intercepts and domain issues, put these on a number line, pick test points in each interval, test for whether it's negative or positive. If or equal to, fill in x-intercepts, fill in negative for less than or equal to, fill in positive for greater than or equal to. and then whatever you get, that's your final answer. So suppose that I'm doing x squared minus 6x plus 8 is less than 0. So I'm going to find my x-intercepts. I'm going to set x squared minus 6x plus 8 equal to 0. So that's x minus 2 times x plus minus 4. And I get x equal to 2, x equal to 4. Put another number line, 2, 3, 4. I'm going to put an open circle on the 2. And I really don't even need that 3 because I just want to really see where the endpoints are. Pick a test point. I'm going to go with 1. I'm going to go with 3. I'm going to go with 5. 1 for each interval. There are 3 intervals. I don't fill in these because it's not or equal to. And then I just check. 1 minus 6 plus 8 is positive. 4 minus 12 is negative 8 plus 8 is equal to 0. So, shoot. I wasn't supposed to plug in 2. I was supposed to plug in 3. 9 minus 18 is negative 9 plus 8 is negative 1, so that's negative. And then 25 minus 30 is negative 5 plus 8 is 3, that's positive. I want less than 0, so I want the negative. So my final answer is 2 to 4. So anything between 2 and 4 is going to plug in to give me that inequality is true. You can also graph this and actually see that the graph looks something like this. And this is not perfect. 1, 2, 3, 4. But it looks something like this. Right? And so we see that between 2 and 4 it's below the x-axis, and outside of there it's above the x-axis.